Hello and welcome to Physics Platter. Today in Physics Platter we will be talking about total internal reflection. In my previous video I have explained the refraction, the laws of refraction and refractive index. Today on the basis of those concepts we will be talking about the total internal reflection. Okay. So we know that when the light travels from a denser to a rarer medium, optically denser to a rarer medium, or we can also say denser, or this can also be written as slower medium, slower medium, and this is faster medium. Means the light travels slower in this medium and then faster in the second medium, or denser to rarer medium. Then according to Snell's law, it was supposed to, let's say this is the point of impact of the incident ray AO. ON is a normal drawn on the surface. Then this AO, the ray of the ray of light was supposed to go along this direction, but it bends away from the normal, right? So when the light goes from the denser to the rarer medium, it bends away from the normal, where this angle I is the angle of incidence, and this angle where the refracted ray makes the angle with the normal on the surface is called the angle of refraction. In this case, when the light goes from the denser to the rarer medium, the angle of refraction is greater than the angle of incidence. Okay. Now what happens if we keep increasing this angle of incidence? Let's say for I1 it goes away from the normal, right? If we increase the angle of incidence from I1, let's say this is R1, and then we move on to I2, then the light will bend even more, so it will go towards this. Alright, that means the light will move even more from the normal. Now if we keep on increasing this angle of incidence, the light keeps on moving away from the normal. By doing this, at some point we will reach an angle. Let me draw it again here. We will reach some angle. Let's say this is a normal. For which the light, the refracted ray will never go out of the surface from the denser medium. Alright, that means the light will reach some point where the refracted ray will move through the surface of the separation between the two media. If this is AO is the incident ray, OB, ON prime, OB is the refracted ray, then angle of incidence, let's say in this case is I, and in this case the angle of refraction becomes, where R becomes 90 degree. Alright, because the light keeps on moving away from the normal when it is refracting from the denser to the rarer medium, we will reach, by increasing the angle of incidence slowly, we will reach at some point where the angle of incidence becomes such that the angle of refraction becomes 90 degree, because it keeps on moving away from the normal slowly. By increasing slowly, it becomes 90 degree at some point. So this angle for which the angle of refraction becomes, so the angle of incidence for which the angle of refraction becomes 90 degree, this angle is called the critical angle. Critical angle. Alright. So critical angle is the angle of incidence for a ray while moving from the denser to the rarer medium, for which the angle of refraction becomes 90 degree. That's called the critical angle. Remember one thing, critical angle can be achieved only when the light travels from the denser to the rarer medium. Why? Because only when the light travels from the denser to the rarer medium, then the light goes away from the normal, and then only it can reach up to the angle of refraction can reach 90 degree. If the light goes from the rarer to the denser medium, we know that the refracted ray moves towards the normal, right? That means the angle of incidence is angle of incidence is actually more than the angle of refraction in case of the light traveling from the rarer to the denser medium. In that case, the angle of refraction can never reach 90 degree. It moves towards 0. Alright. So, to reach critical angle, the light must move from the denser to the rarer medium. Alright. Now, what happens if we increase the angle of incidence further? By the way, this angle of critical angle is sometimes written as theta c or IC. It is generally denoted by IC or theta c, c for critical angle. Alright. Now, what happens if we go further beyond critical angle, beyond theta c? What happens after that? Let's say the light travels in such and falls in such an angle of incidence I. This is N, A, O. This time let me write O here, N prime. What happens if the I becomes greater than the critical angle? In critical angle, the incident ray was going through the surface and the angle of incidence, the angle of refraction was 90 degree. But after critical angle, if the angle of incidence is more than the critical angle, the angle of refraction becomes even more than 90 degree. But if it becomes more than 90 degree, the light never leaves the first medium. That means it comes back to its previous medium again, right? That means it gets reflected to the previous medium again, right? That means the incident ray gets reflected and the reflection occurs. The reflection of light occurs at the surface of separation between the two media when the angle of incidence is more than the critical angle. Alright. But how will it get reflected? Of course, when the light gets reflected, it must follow the laws of reflection. It must follow the laws of reflection. Okay? And this phenomena is called the total internal reflection. Total internal reflection. And when the reflection happens, the angle of incidence becomes equals to the angle of reflection. Here R is the angle of reflection, not refraction anymore. That means when the light falls or the angle of incidence, with the angle of incidence more than the critical angle, there is no more refraction, there is no more refraction, there is reflection instead, and the light gets back to its previous medium following the laws of reflection, and that is called the total internal reflection, because the whole light energy is going back to its previous medium, which is a denser, there is a rarer medium. Alright, and that's called the total internal reflection. Okay. So what are the examples of the total internal reflection? total internal reflection is generally used in the fiber optics, where the light goes in and falls on the surface of the fiber at an angle more than critical angle and gets totally internally reflected, and then again it keeps on falling on the surface with the incident angle more than critical angle and keeps on getting reflected, and thus the light ray never goes out of the fiber. Alright, this way the total optical information travels through the fiber, and it's very fast because it travels almost at the speed of the light, which is very fast. Another example can be mirage, which we often see on the streets, if not on the deserts. What do we see on the streets? Sometimes if you go on the street and it's a sunny day, if it can happen also when it's not so sunny, generally in the warm days, if you go out on the street and we can see that while traveling on the street in front of us, we can see that there looks like there is some water on the street, and then the objects in front of us gets reflected. Let's say there is a truck, and if we stand somewhere here, sometimes we see that it looks like there is water and we see the reflection of the truck. We see the reflection of the truck on the street. But if we go closer, if we keep on traveling and go closer, and this water disappears, right? So actually there is no water. This is nothing but the optical illusion. Optical illusion. And that's happening only because of the total internal reflection, right? And same thing happens in the deserts. How does it happen? And this is called the mirage, of course. This is called the mirage. This illusion is called the mirage. How does it happen? Alright, on the street, let's say this is a street. Let me draw it a little bit longer this time. Let's say this is a street, and when the sunlight falls, let's say there is a truck here or a tree. Let's say there is a tree here. There is a tree here, let's say. Okay. So how do we see things? We see things because the sunlight falls on the object and it gets reflected and comes to our eyes. Let's say this is me standing there. Alright. So sunlight falls and then it gets reflected by the object, and then it comes to our eyes and we see the object. That's how we see objects. But sunlight also falls on the street, and the street becomes warm and warmer and warmer with the sunlight. That means the layer of the air which is close to the street is warmer, which also means that the density becomes less of the air which is close to the street. If we go to the next layer of the air, it gets a little bit less warmer. That means it is a little bit denser. If we go slowly upward, the air density becomes denser and denser. So density of the air is decreasing slowly in the downwards. That means it is increasing upwards. The uppermost layer is the denser ones, and then the layer which is close to the street is less dense. Or we can say that the rarer mediums are near to the streets, and then the layer of the air becomes denser and denser when you go upwards. Now when the light falls on the object and gets reflected, it goes through air, of course. It gets reflected in all the directions, right? So let's take a ray which goes in this direction. On this layer it falls at an angle of incidence I, right? But to the next layer, when it goes to the next layer through this surface, it goes from the denser to the rarer medium actually, right? That means the angle of refraction becomes greater in this case. That means the light moves away from the normal. Then it falls on the next surface and then it moves even further from the normal, because again it falls from the denser to the rarer medium, right? In such a way, the angle of incidence keeps increasing. See, here it was less than here, and in the next surface is even more. The angle of incidence is more. In such a way, it keeps on increasing, and at some point it reaches the critical angle. And at some point to the next layer, it goes to more than critical angle. More than critical angle. So, it becomes more than critical angle. And then the moment it becomes more than the critical angle, it gets totally internally reflected. And then it comes to our eyes. Okay. See, the light comes from the object, the reflected sunlight from the object comes and gets refracted by the different densities of the air, and then at some point it reaches, the angle of incidence reaches more than the angle of, becomes more than the critical angle, and then total internal reflection happens, and then that total internally reflected light comes to our eyes. But our eye cannot track this line of ray because it can see only the straight lights. For our eyes, the light travels in a straight line and we see the last part of the light only. That means this part of the object we will see somewhere here. We will track down in the straight line and we will see somewhere here, right? That means the object will become upside down, and then we will see that it will look like to us that there is some water, and then the object gets reflected, the image of the object gets reflected and comes to our eyes. That's how we see the things upside down on the streets, especially on the warmer days, right? And this is called the mirage, and this is how the mirage happens in the deserts also, because the sand becomes very hot and the air density, the change in the air density becomes more visible, right? And that's how the mirage or the optical illusion happens. Here I would like to show you quickly how to calculate the critical angle for, let's say, water. Alright, for that, let's say the ray of light is going from water to air and it falls at an angle which is critical angle. The angle of incidence is critical angle, which is theta c. That means, let's say the AO is the incident ray, that means the angle of refraction will become 90 degree, that is R equals to 90 degree. Alright, this is water whose refractive index is 1.33 and the light goes from the water to air whose refractive index equals to 1. Alright, so in this case from Snell's law we can write that mu of water into sine of the critical angle theta c equals to mu of air into the sine of the angle of refraction. That means mu of water is 1.33 sine theta c equals to mu of air is 1 into sine 90 degrees. Now sine 90 degrees is 1, we know that. Therefore, we can write sine of theta c equals to 1 into 1 divided by 1.33, which gives us theta c equals to sine inverse of 1 by 1.33, which is approximately equals to 48.75 theta c. That means the critical angle for water is 48.75 degrees. Alright. Okay. So this is how you can find the critical angle of any material when the light goes from that material to air, because the refractive index of air or vacuum is considered to be 1. That's a standard one. Alright. Okay. So I hope this video is a little bit useful for you. We will meet up in the next video with some other topics of physics. Alright. Till then, take care.